Hey everyone, this is Matt with Learn Everything About Design, and in today's video we're going to be using the Revopoint MetroY Laser 3D scanner. We're going to walk through the process of setting up a part, scanning, and the main focus of this video is talking about how to get the best possible scan out of the MetroY, but really any of the Revopoint scanners. So what we're going to cover today is going to be the settings at the scan level, so basically the point distance that is going to control the display that we see when things change color. We're going to talk about the fusion method, so basically picking the distance between the points when we're turning that raw point cloud data into a more structured point cloud data. And then we'll talk about all the settings for points, things like isolation detection and overlap detection, smoothing and simplification. And we'll do the same thing at the mesh level. So we'll talk about the mesh settings, basically the quality setting, which dictates the size of the triangles or the polygons. And we'll go through the process of looking at the difference between things like smoothing a mesh versus smoothing the points. So hopefully at the end of this video, you'll have all the information you need to understand basically what these settings do at the start of your scanning process, how they affect it when you do things like fuse a raw point cloud, and what settings you can use to get the best possible quality mesh out of RevoScan software. So while we are focusing specifically on the MetroY today, it does apply to the MetroY Pro, the Metro X, the Morocco, the Inspire, the Range, basically any of these scanners. The settings are going to be somewhat universal. So if you understand the basics that we're going to cover here today, that should help get a good quality scan out of pretty much anything you're trying to scan. Now, the part that we're looking at today is a stamped metal cover. It's powder coated, so it has some orange peel on it. And it's also quite old, so there are some sections that have like a little bit of rust on them and corners that just aren't going to scan very well. The intent of this video is not to get a perfectly good 3D scan of this part. We're going to focus our attention more on what the settings do and the differences between that. So we'll get to see how we can handle things like removal of marker dots and what some of those settings do. Also how we can use these settings to do things like smooth the points and smooth the mesh to get a smooth result rather than having that bumpy sort of wavy result that I get a lot of comments and questions on. You know, how do we get a good quality scan? Everything I do looks kind of bad, looks kind of orange peely, looks kind of bumpy. So this video, we're going to talk about all that. This is actually the third or fourth time I filmed this. I keep having microphone issues dropping out, so I don't have anything set up here to scan. I've already actually recorded all that, so hopefully the audio catches this time. But just a quick reminder, we are a Revopoint affiliate on the channel, so if you are looking to buy, we do have a discount code, which will save you whether or not you use our link. We also do have an affiliate link, so if you are buying from Revopoint and you want to support the channel, you can use the discount code and the link, and that will save you a bit of money, but it also will help out the channel. All right, so without further ado, let's get this part set up, scan it, and then we can get back to the desktop computer and we can go through the processing. Okay, so since there was about 20 minutes of audio that didn't get recorded, I need to narrate this part. So the first part of any laser scan is to make sure that you have enough marker dots so that you can actually scan it. You want to make sure that there's at least 5 in view at all time. And in this case, make sure that they're not too close to the corner. Remember that when we have marker dots, they're going to appear different in the scan data. So they'll be raised up a little bit. And with Revopoint, there is an automatic sort of marker removal option that we'll talk about a little bit. But that leaves a hole in the point cloud, which can get filled later on in the mesh stage. But I find it's a bit easier to manually remove those and smooth them a bit later. But just something to keep in mind. Now, we have a small, basically a mouse pad here with marker dots on it and a couple of tiny black caps to raise the part slightly off of it. This really helps because that way when you go to clean it up, because at this time there's no automatic base removal for the laser scan modes, this helps because you can just easily just kind of delete that bottom piece. Now, for the actual scanning part of this, we do 3 scans for this part. So initially, all of them are going to be cross laser line. So it's going to keep that consistent. If you were used parallel or single line, much of the same settings would still apply. You're just pulling in less data, which means that you can focus the laser line in certain areas a bit better. So generally, parallel lines work really well when you need to get corners or edges, whereas the cross line might not be as efficient with that. But this first scan, we have the basically the target point distance set to 0.15. Now, this setting doesn't necessarily mean that you're going to get a higher quality point cloud and a higher quality mesh. What this is doing is dictating when the color on the screen is changing. So what we'll see with this part is that scanning at 0.15, we're going to scan at 0.5 millimeters, and we're going to scan at 1 millimeter. At the end of this, we would largely have roughly the same number of frames, which means we've captured the same number of parts, which means that we can use very similar fusion settings and mesh settings. So when you're thinking about a part, you need to look at the size of the details you're trying to capture and kind of decide what size point distance, that target point distance, is going to be. Because again, it doesn't dictate really the final result. It's going to dictate when the color on the screen changes. Now, again, I captured basically the same number of frames. I think the 0.15, we captured about 8,000 frames. The 0.5, we captured about 7,000. And then the 1 millimeter, just a little bit less than that. And so at the end, really what we're looking at is when the part on the screen is going to change to green. And that's all the setting is really doing. With all of these, you still need to have marker dots at specific distances so you can see at least 5 at all time, because we're not trying to perfectly replicate this part and get the inside and the outside. I'm not really worried so much about all the details, but I wanted to highlight, essentially with all of these different settings, the 0.15, the 0.5, and the 1 millimeter, you almost need to scan for the same amount of time to get these minute details in the corners and the creases and things like that. The big areas will turn green much quicker, but the areas like rotating the scanner down at the side at a steeper angle, trying to get into those corners, those areas are still going to take a good bit of time. Maybe not as much time because, again, we did capture fewer frames, but maybe not as much time, but it is still going to take fairly similar amount of time if you have a part that has a lot of detail. So, these corner details, these recesses, this part being a stamped steel part doesn't have a lot of like casting marks or anything like that. But those are just considerations that we need to think about. For a part like this, my gut reaction would be to use 0.5 millimeters. That would be enough detail that I would make sure I captured enough points to get a good quality mesh downstream. But any of the settings, the 0.15, the 0.5, or the 1 millimeter would be perfectly fine. Now, keep in mind that we are not going to get a great result on the edge because the edge was very close to the desk or the workbench. And without scanning this in multiple positions, we're really not going to capture those details. Again, not the point of this video, but if we were trying to do this part, I would scan likely at least 3 times, the outside, the inside, and then a orientation where I would do both so I could get outside, inside, and then an edge so I could have something to align them. So let's go ahead and talk about processing. Okay, so now that we're back at my desktop, let's go ahead and talk a bit more about the processing side of things. Now, I've done a little bit of work before this. So essentially what we have is the 3 scans, the one that was set at 0.15, the one that was set at 0.5, and the one that was set at 1 millimeter. And with each of these, I went through the process of doing the point fusion, and then I removed the base, just simply to speed things up and clean it up, because the time it takes to go from the raw data and fuse it to basically the next step of that point cloud can be time consuming, especially when we use really small settings like 0.15. And there's really no reason for us to sit through that. But what I do want to talk about here is what these settings do for fusing the point cloud and how they have an impact on your actual raw data. So if we look at the raw data for this one, for example, remember it captures the mat, the desk, because at least at the current time, there isn't an option to automatically remove the base that I've found. Hopefully that'll come out in the future because it is available with other scanning modes like full field with the Metro X and the MetroY Pro. But for the MetroY and for just the general laser scanning settings, I haven't found that option. So again, when we set this up, what we did was we put it on a couple of little caps just to keep it up off the base. Now, I didn't raise it up too far because I wanted it close to the marker dots. But what we can see here is that in the raw data, the marker dots are captured, but they're raised up and it creates a bit of noise here.
All right, and so when we have this raw data, we've got tons and tons of points. We've captured, at this point, if we look in the bottom left-hand corner, almost 8,000 frames. So with all of that data, when we go through the process of fusing it and essentially taking the raw data into a cleaner version of that point cloud, we need to have a good understanding of what these settings do. First, I never use the fast fusion method. I think that this would be okay on basically parts that don't have a lot of detail. Probably not stuff that you're laser scanning. So if you're doing something like scanning somebody's face with a Morocco scanner or the Inspire 2 on full field or something like that, or some sort of general objects that you don't really need that high detail, fast fusion can help. But there is a different algorithm that's used for fitting the points when you're using the high quality fusion. So for anything that you're laser scanning, you're likely just going to have to suck it up with the time that it takes and use the high quality fusion method. You'll get a much better result. The next step is the point distance. Now, this is actually really important because the point distance does not have to exactly match your scan settings. And generally, there'll be a recommended number. You can see 0.14 is the recommended number here based on the number of frames and ultimately the raw points that we've captured. And what this is really looking at is how dense is the raw data that we've captured. It's not going to give us a recommendation where, let's say that there is half a millimeter or a millimeter between these points. It's not going to recommend that we fuse it down to 0.14 or 0.15 because it's just not realistic. But if we've captured more data, so essentially if these points are really close together, and if we take a look at it, it's a pretty nice uniform grid. If these points are really close together, then we'll have a lower value recommended for the point fusion. That doesn't mean that you have to stick with it. Generally, you don't want to go below that recommended number, but you can certainly go above it. And so this first scan was done at 0.15. That was the setting that was used in the scanner, which means it's not going to change the color to green until we have the density that matches that 0.15. So again, the recommended number here was 0.14. The remove markers option, what this is actually going to do is it'll find the markers in the scan and it will remove them, leaving a hole behind. Now, while I think that this is an okay option, I really wish that it would fill the holes back in with points when it's doing the fusion. So unfortunately, I generally leave this option off and I manually remove and smooth those areas out when I'm doing either point simplification or point smoothing or at the mesh level. I find that it just gives me a better result. But if you do toggle this on, what you're going to end up with is going to be holes everywhere there is a marker dot. It's not always perfect, but in general, that's what you'll get. Now you can see the result here looks really noisy. And this is probably what most people are seeing because they'll go in, they'll set that scanner setting as low as they possibly can, thinking it's going to give you the best detail. And what you end up with is a lot of noise. And that's because the points are so close together. If we get really far in here, the points are so close together that you get all of these little basically peaks and valleys that happen. And with those peaks and valleys, you end up getting essentially a messy scan because it doesn't do any sort of smoothing. Now, if we go to the scan where we had a 0.5 millimeter spacing, now the 0.5 millimeter spacing, the raw data looks very much the same as it did at the 0.15. Now, when we go to the fusion setting, you'll see here it's recommending 0.17, which means even though we set that number at 0.5, I scanned enough. You can see here that we've got 71,000 points in the fused version, but if we go to the raw version, we captured almost the same number of frames, about 7,000 frames. We captured 8,000 in the lower setting. So essentially, we have almost the same data. It's just recommending 0.17 instead of 0.14. So when we take this and I fused it, I actually used a fusion value of 0.5. I matched the number I set when I was scanning. Now that's not strictly required, but the reason I did this is because I wanted to show you that we still have, if I zoom out a bit, we still have all the detail we need in these corners, these sharp corners here, and the detail on the ridge here. Now it hasn't been converted to a mesh, obviously, so we are going to still see some sort of, jumps or rough edges because of the orientation of the scan data. So you can kind of see that it looks like basically wood grain or something like that. And so with the scan at 0.5, the scan setting at 0.5, and fusing at 0.5, we captured it a little bit faster, and it fused quite a bit faster, and the result is actually more accurate. So let's try to see if I can get to the zoom. So this is actually a better representation of the orange peel in the powder coat than the 0.15 version. The 0.15 version just kind of looks like a textured surface or like a stucco or something like that. Now, the version of the scan that was done with the 1mm scan setting, again, based on the number of points that were captured, you can see that we did 6,500 frames. So again, we were at about 8,000 for the 0.15, we were at about 7,000 for the 0.5, and 6,500 for the 1.0. So in terms of the data captured, it's almost identical. It's very close to the same. So if you zoom in, you're going to see tightly spread points in there, and ultimately the data is very similar. The recommended fusion value here is 0.19. So again, 0.14, 0.17, 0.19. They're all really close relative to the scale of the object. And so if we had just scanned it at 0.5 millimeters and had that one scan, we would be good to go. And in this case, the 1mm is also a pretty good representation. Now, when I fused the 1mm, I didn't use the recommended setting. I used 1mm. Now, when we use 1mm, this is the point where we're going to start to lose detail. So you'll notice things like the detail in the holes is a little bit different because there's not the same amount of points around the hole. So you'll notice the holes start to lose detail, but the recesses are still pretty good. You'll notice that if I zoom out, you notice that we still have fairly good detail in some of these areas. Now, all of this is to say that if we had just scanned it at 0.5 millimeters with the amount of time we spent scanning, and we played around with fusing this at different values, we wouldn't have had to scan it at 0.15 or 1mm. So all it's to say is that initial setting, that 0.15, the 0.5, the 1mm, that is really impacting the graphic preview that we have. And it doesn't necessarily mean that you're going to capture or get a cleaner scan or more data on the back end. It really only comes down to the number of frames we capture, but that number is going to indicate graphically on screen when it captures enough data to be able to do the point fusion method at that value. And so again, that's why we saw 0.14 for the recommendation on that initial one. Now that we hopefully understand that, the next step in this process is to do some of these other steps in the point cloud area. So we've got isolation, overlap detection, smooth, and simplify. In addition to smooth, we also have a smoothing brush that we can use over here. Now, what I will say is that we also need to be careful with how we approach these settings, because some of them, like simplification, I found will give us a worse result when we move to the mesh. Now, for this example, I'm going to start with the 0.15 version. Again, this kind of looks the messiest. It's got the most amount of noise here. So the first thing we do is isolation detection. And essentially, I use the default value 15% almost all the time. This will find if there are any points that are kind of floating outside of the realm of the bulk of the rest of the scan. And that's where this 15% comes in. So if there are little groupings of points like around this hole that aren't necessarily connected, then it's going to find them and select them. And when we hit apply, it's going to delete them. So that's the first step to cleaning things up. Now, this doesn't always mean that it does it right, because you can now see we're missing some data here. So you can always undo. You can go back and maybe reduce this number if you felt like it was taking too much, do the detection again, and do the apply. Because I'm not really concerned with getting a perfect scan of this part, I'm not going to spend a ton of time here, but these are all the settings that we need to go through and understand. Overlap detection, again, another important one. What this is looking at is going to be the vertical distance. So if you think about your scan basically we're just using the laser and we're scanning a bunch of points. A lot of times what's going to end up happening is we get points all over the part, like what we would expect to see, but sometimes we'll get points that are just a little bit above in Z because of reflections or lighting conditions or something like that. These often will contribute to the noise of a scan. And in this case, we don't actually have very many, but these are areas where we've got extra points on top. Most of the time, this actually ends up coming from going back and rescan, or at least I found it comes from going back and rescanning the same area again. So, for example, on this part, if we were missing data on the side and I went back and I tried to rescan it, that's where I'm going to start to get some of those overlapping parts. The next setting here is smoothing. Now, smoothing is something you need to be very careful with. I personally will go and smooth and work with the mesh more so than the point cloud. Now, if you go through the point cloud, set the scanning and the point cloud fusion and all that and use reasonable numbers. So again, the 0.5 millimeter or the 1 millimeter, you already are starting with a relatively clean point cloud. The smoothing option here can be very destructive at the point cloud level. So the strength value, this is going to determine how far the points can move, and the times value is going to dictate the number of times it repeats this process. So if you think of 3 points that are building basically a triangle and we want to smooth it to flat, if we have a high strength value, it's going to be able to flatten them out more or move that point more the first time through. Now, if we have a very low strength value, but we go through it 50 times, each time it's going to move that point a little bit more each time. It's just going to keep going until we get that smooth result. Now, the reason this is important is because the strength, cranking the strength all the way up oftentimes can reduce detail on edge features, for example. So if you've got a tight crease, like over here, we might lose detail if we use too high of a strength value. So what I'm going to do is smooth this with a low strength value and a high number of times. We're going to apply it, and then we're going to take a look at the result, focusing on this corner, and then we're going to undo it and switch those. We're going to increase the strength value and reduce the number of times. Keep in mind that this is looking at the spread of the points in basically the raw data, not the raw data as the stuff we scan, but what it's currently at. So you can see if I undo and redo, you can see that it didn't make much of a difference in terms of the overall geometry. The corners are still very much the same, but you'll notice that a lot of the noise, so basically what looks like that sort of stucco or that textured area, a lot of the noise is getting reduced. All right, so if you're using the smoothing, making sure that you do it with a high number of times but a low strength can oftentimes help preserve these features. Now, if we flip that around and we say, all right, well, go crazy. I only want to go through this once, but the strength can be 20, and I apply it. Now what we're doing is we're giving it the freedom to move points quite a bit more, but we're only letting it go through once. All right, so you can see here that it looks more melted, and the corners have seemed to have lost a little bit of detail. So if I undo this, you can see that it was much more aggressive, even though it went through just once. And again, you can play around with where these are. If we crank both of them all the way up, we set the strength at 20 and the times at 50, it's going to do that pretty extreme modification to where the points are, and it's going to run through it 50 times. Now, I will say that over the past year or two, I think the back-end processing or the algorithm for this has gotten better to the point where we're not so destructive on these sharper cornered features. But it really is looking at, even though we don't have triangles, it's not a mesh yet, it's really looking at angles, kind of the height average in an area. And as we go around corners that are very smooth, like this part is stamped. So as we go through those corners that are very smooth, what we end up getting is essentially just a smoother, more melted version of it. All right, so going through, you can see that it did a really aggressive job of smoothing this thing out. It did still preserve a lot of those tight details in the edges, but it may be too aggressive if you're trying to, say, reverse engineer this part. So if I undo that and we just take a look at the difference, you can see how much sharper and crisper these corners are. And when I redo that, you can see how much more melted it looks. So while the scan looks smoother and looks cleaner, it is probably going to be too aggressive if we're trying to replicate this part. So my suggestion is always to reduce the strength and have the strength value lower and have the number of times that you iterate through higher, because it'll do a better job at preserving those corners. But if you just go all the way to the right with both of these sliders, it's going to be most of the time too aggressive for mechanical type parts. Now, if you have a very organic shape and you're not too concerned with preserving sharp corner details, then you might be okay. So you can see here 50 times going through, strength of 5. That did a relatively good job here. All right, so the next thing that I want to talk about is some of these holes that are in here. We don't really have anything that we can do with that until we get to the mesh stage, but we do have the option to use a smoothing brush, which allows us to basically, let's see if I can get it in an area where this will make sense. Let's try this one here. So if I kind of go over this area, maybe go over this one too, this is a way that we can take those marker dots that are here and we can kind of smooth out the results. It's not going to be perfect, but it's going to get us a bit closer. So as we rotate this around, the marker dots areas, you can see here, those are a bit smoother. All right, and the last thing that we have in the mesh section, but with the exception of merge, is simplify. Now, again, simplify is one of those things where I generally will not use it on a part unless I have a very good reason to. I think that it's much better to simplify at the mesh level after we've converted the high density point cloud into a mesh. Then we can go through and remesh it at higher or lower numbers. We can simplify it and smooth it. And I found it to be less destructive to the shape. But if you want to play around with it, you've got two options, a uniform and geometric. Now, uniform is going to try to keep the same size triangles or polygons across the entire part. I have not found a use case where that makes sense. In most cases, you're going to use geometric. And before I do this, I generally will go to display and try to enable the points. Now this works a little bit better when we are at the mesh level because we can turn on the mesh edges and stuff. So if we zoom in, you can kind of see the point spread. We got a lot of dense points, and then we got some kind of open areas where the angle of the scanner was. So if I apply this, again, we can undo this. So while it is destructive in nature, we do have an undo option. And so if I zoom back in, what you'll see is we get this sort of patchy nature. So we got a bunch of areas where it's reduced that, and then we got areas where we still have this high density. And these are likely areas where we don't have overlapping points, but we do have basically a more dense section. So if you continue to go through this and you apply it again, or you increase the ratio or decrease the ratio depending on your goal, you can still get to a good representation of the part. But what I have found is that when we take this over to the meshing stage, it generally does a worse job meshing, because instead of having a nice, it's not really looking, there we go. Instead of having a nice consistent grid of points, you now have these pretty far spaced apart points, and you've got some really tight points. So what I'm going to do with this example with the 0.15, because this is not the settings I would use for this part, I'm going to go ahead and take this to mesh. We can see how it does. All right, so once again, we've got fast meshing and we've got high quality meshing. Now, I would suggest high quality again, because if you're using a laser scanner, you're likely trying to capture more detail on a part, and you likely want a bit more control. When we go to the high quality setting, then essentially what we're going to be doing is giving ourselves more control over what happens. If you don't want any of that, you can always just do the one-click option and let it go through the points and the meshing all by itself. Now for us, the first thing we need to think about is the grid size. Now remember, this part was scanned with the setting at 0.15. It was fused at 0.14, and we did some stuff to it. We manipulated the point clouds, and now we've got areas where we know the points are farther apart than 0.14. All right, so we got these big gaps here. What we have for the quality setting, the grid size, has a direct impact on what the final mesh is going to look like. If you make the grid size too small, you're still going to get a very noisy mesh. You're not going to get something that looks nice and smooth. And that's probably where most people are getting hung up. So this grid size, if we don't have points that are that close together, let's say we don't have points that are 0.1, 0.09 together, what ends up happening is it's going to make a triangle, and then it's going to make smaller triangles in those areas. So if we try to mesh it at this level, we're likely going to get a bad result. So what I'm going to do is I'm going to take this a bit higher, and I'm going to go to 0.2. Now remember, scanned at 0.15, fused at 0.14. Now I'm taking this quality setting and I'm making it slightly bigger. Now that's not universally true, but again, we can remesh this and we can see the result. But I'm going to start at 0.2, very close to my initial settings, just slightly larger. When you're trying to figure out what these numbers should be for the initial scan setting, for the fusing, and for the quality, you really have to look at the detail of the features that you have. This part being stamped steel likely doesn't have any really high detail requirement features. So what you can do is you can go in and you can, again, mesh this, play around with it. The larger the grid size is, the faster it's going to mesh. So if you're going to play around with it, I would start with a larger setting. So if I go into display and mesh model display and I do the wireframe overlay, we can kind of see what we're working with if I zoom in here. So you can see those areas where we did that simplification, we've got these large triangles, and the areas that were still fairly dense have these small triangles. This right here is not a great result for a mesh. While it might give us a decent output, it doesn't make a whole lot of sense to do that, which is again why I generally skip the simplification of the point clouds. I find that it just gives me a worse mesh to go on. Now, we still have the same tools like isolation. You'll find very few points that show up with this. I'm going to go back to my display and go back to solid for this. And then the next step is hole filling. Now, currently the only holes we have are actually supposed to be there. But if you did use that marker removal, or if you want to clean up where these markers are, we can go into the mesh and we can, let's say, select and hit delete or click the trash can icon, get rid of that. And then for the filling, we want to use a curved method because this part isn't completely flat. We're going to detect the holes. It's going to process this, has a bunch of like little holes around the side. But we want to select the hole we want and select apply. Generally, I don't do select all. But you can, if you have a part with a bunch of little holes, you can certainly do that. Now, if I go back and I show the wireframe overlay and we take a look at where the hole was patched, again, this is different. This looks different than the mesh that's surrounding it. So this is something to keep in mind, that when we do things like simplification or when we're starting to begin to fill holes, the underlying mesh is going to start to be different. So if we continue this process, there's another marker here. We'll delete it. There was one over here. Make sure you get enough. There was one here and this one here and so on and so on. Then we can detect those. We can select them. We can fill them. And it's important when we're going through this process that we do this in order. And when I say in order, what I mean is kind of the way the tools are laid out left to right, with the exception of merge. Merge I generally do at the point level and then rerun through isolation and overlap detection and smoothing if we need to. But once we've gone through this, again, filling holes and isolation, I'm going to go back and show the wireframe overlay again. Again, where the holes are, the density of the mesh is different. We can run through smoothing if you want to. You're going to have the same settings. Again, the strength and the times. I would still here say that lower the strength value, increase the number of times that it goes through. And then simplification is kind of this last step before we export. Now, what simplification is going to do is it's going to take a look at the mesh density. So let me rotate this around so we can kind of see an area like, actually, let's go over here. Let's look at this corner. All right, so these areas where we've got sort of a filleted corner up here, and then we've got some flat areas. When we go through the simplification process, let's say that we want to take it down to 50% of its current mesh value. So we've got almost 1 million polygons. So we want to take it down to about 450,000 polygons. What it's going to do is areas where we've got high changes in curvature, so it's looking at the angle between the meshes, it's going to keep the density of those meshes higher in those areas to capture the geometry. Areas where we've got low change in curvature, so let's say areas where we've got flat spots, what it's going to do is it's going to make larger polygons in those areas. So I'm going to take this to pretty extreme. I'm going to go up to 80,000. And this is an area where a lot of people make mistakes because they think that keeping a larger mesh count is going to give you a better result. Now, oftentimes the larger mesh count is going to do things like bog down your CAD system later on. It's not generally going to give you a higher quality result. It's in most cases, it's going to give you a worse result. Now, this is by no means perfect. And again, that 0.15 is not the setting I would use for this part, but this just goes to show you that going from the original raw data that again kind of looked like somebody sprayed it with spray paint that cured before it hit the part, to the few settings with a little bit of smoothing and cleaning up, to the meshed version of this, we were able to get to a reasonable result. And if we take a look at the underlying wireframe and we zoom in, we can see that we've got fairly large triangles or polygons in areas that are mostly flat. And then if we zoom in to areas where we've got higher changes of curvature, like these corners, you can see the density is higher there. All right, so now that we've seen that with the 0.15, let's go ahead and repeat the process with the 0.5. So again, isolation detection. Generally, I'll use the default settings, 15%, 10%. It's going to be mostly the same. Overlap detection. And then smoothing if you want to use it. Now, in most cases, if I do smoothing at the point level, it will be very minimal. So again, I'll run through 50 times, but the strength value will generally be fairly low, between 1 and 5. You can see even 5 here, I feel like that was way too aggressive. So I'm going to undo. Because we don't have the same density of points that we did in that first example, because we have, in this case, 70,000 points. If we go back to the fused version of this one, we had 285,000 points. So when we only have 70,000 points, using smoothing to move those points a good distance is going to give us a bad result. So I'm going to apply it with the strength set to 3 and times at 50, and just watch in this area over here. So this looks okay. When it was set to 5, it was a bit too aggressive. Again, I'm not going to simplify because I want to keep the density of the points fairly uniform across the part. I don't want to have those areas of low density. While you can get away from it when you get to the simplification process, I find it's a bit better with meshing. Now, once again, the grid size is important. You need to have the grid small enough to capture those small details, but high enough so that it doesn't take a large amount of time. Just to show or to highlight this, I'm going to use the exact same setting, the grid set to 0.2. And the reason for this is because the original scan scanned at 0.15, this one scanned at 0.5. On the lead-in side of it, it was scanned at 0.5 and it was fused at 0.5, where the other one was scanned at 0.15 and fused at 0.14. So the result of this one, to me, is a much better looking mesh. It still has some noise in it. We still need to do some smoothing and cleaning up those scan dots, but you can see that the consistency of the triangles across the entire part is much better. So I'm going to go to display and I'm going to turn that off, and I want to get rid of these marker dots. So again, this is something that we need to do. We're going to just select and delete, and we'll do that over here as well. And remember, this part has just a very slight curvature to it, so we can't use a planar hole filling. So we're going to go through there and clean those out. All right, so now that I got those, double check isolation and overlap detection. So no data found, that's good. Then we're going to go to fill holes. Again, I'm using curved because the part has a little bit of curvature to it. I could spend some time doing things like cleaning up these holes, but I don't really feel like we need to for our example. We'll apply this. Again, the density of the mesh in those areas is going to be different. You do have the smoothing brush, so if you want to smooth an area, you can. So you can see that I was able to smooth around there. The orange peel, we're going to get rid of. We're going to clean it up with smoothing, but just, again, you can use these tools. Generally, the smoothing brush I use if I have problems removing marker dots. Sometimes when they're close to edges or corners, you'll just get in trouble. Try to avoid that as much as possible. Again, I'm going to use kind of the same settings, 19 and 0.2. And you can see there's a little bit of orange peel. We can rerun it again to try to smooth it out again. And again, you can just continuously run it, making sure you're not getting to the point where you're degrading the data too much. I think this looks pretty good. Just to show you, I'm going to go ahead and crank the strength all the way up and apply it. It's not going to have near the impact on the shape at the mesh level as it did at the point level. When we tried to use smoothing at the point level and cranked it all the way up, it had a very big impact on the results. Now that we've got a true structured polygon wireframe, it's not going to have the impact that it did to the sort of raw points. So you can use a higher strength value if you need it, especially if your part has a lot of discrepancies in that surface finish. And then the last step in this is to simplify. Now, again, the simplification, I don't know why I keep turning this off. Let's go ahead and turn it back on. The simplification, the idea here is to reduce the size or increase the size of the polygon, so reduce the overall count in areas of low curvature to the point where it makes sense. So right now we've got 267,000 polygons. I'm going to take this up to 60% and apply. And what we should see is that the big broad surface, we're going to get those large triangles, and in the corners, it's going to keep the higher density. This is really apparent in this area here. So you can see the fillets have a pretty dense triangle structure, and then in this sort of flatter section, we've got larger triangles where we can. I'm going to go ahead and go back to display and go back to solid. All right, so this is a pretty good result. I could spend a little bit more time cleaning things up, but for the most part, we went from the raw data, which again kind of looked like this, even though it was scanned at 0.5, it still had a lot of that noise in it, to the fused data, which looked a bit better, and to the mesh data, which is quite a bit cleaner. Again, I can't stress this enough that every time you do processing of the raw data, you do need to just be very careful and pay close attention, especially in sharp corners or tighter transitions, what is happening when you do things like smoothing and simplification. So now we've got a file here that is down to 100,000 polygons. This one here, 285,000. You can see it's missing some data on the side because we weren't able to capture it. This one here, 100,000 is pretty good result for this part. I'm going to go to this last example. So this one was scanned at 100,000 or 1 millimeter. Overlap detection, nothing found for that. Smoothing, I'm going to go ahead and just apply it because we applied it to all the others. And then meshing, I'll use the same 0.2 millimeter setting. I'm just going to carry that across so we can kind of identify the difference. Now that we're going to a file that was fused at 1 millimeter, this is where we're starting to see a big difference, right? So when we took the 0.5 millimeter one, which was fused at 0.5 millimeter, and we meshed it at 0.2, it still had enough data to make that work. Now we're getting to the point where we don't really have enough data to make it work. So in this case, the grid size probably needs to be higher, more like 0.5 millimeter, and we're gonna redo the mesh. So it's gonna overwrite the mesh back from the raw data. And you can see it still just doesn't quite have the resolution. If we go back and we like turn on a wireframe display, you can already see the triangle size is quite a bit larger at this stage. And if I try to make it smaller, so let's go down to 0.1. Let's just go pretty extreme. Now what's going to happen is RevoScan needs to fill in all the missing data. It needs to guess what was there because we basically have points that are millimeter apart, and we're saying we need to make a grid that is 0.1, a tenth of that, and it has to guess what's happening. So if I zoom in, like in this corner here, it's basically trying to guess and figure out what happened here. So let's just go back to the other extreme. Let's go to 1 millimeter around there, apply it. So the grid size, you can see it's not really changing that much in this area in terms of the size of the triangle when we go from that to this, because it doesn't have any extra data to figure out to sort of fill in that gap. So it's largely going to be the same, and it's only going to be able to capture as much detail as we give it from that point stage. I'm going to go back to display and turn this off. Now, the good news here is even though we scanned it at 1 mm, the raw data, we had enough there that we could go back and go to the fusion stage and fuse it at a much smaller number and capture that. So if I just repeat the entire process and I fuse this at 0.2, what's going to happen is it's going to get rid of the mesh we created. It's going to get rid of any changes that we did to the fuse point cloud. So isolation, detection, overlap, smoothing, any simplification, all that's going to go away. But what it's going to allow us to do is go through the process and say, oh, well, all of the settings I used, I just picked too large of a number. I scanned enough data. I have all the raw data I can always go back to, but I fused it at too big of a distance, or I meshed it at too big of a distance, or something like that. And you can always kind of work your way back as long as you have enough scan data, which is why it's important to always scan more than you think you need. That way you can always go back and make changes. This fusion process, right now I'm running this on my desktop, which is a 10th gen i7, and the performance check told me that it was poor performance. It wasn't going to work to scan with the MetroY. It still is processing fine. It is still using the CPU and the GPU and doing all that stuff. Just in terms of capturing data is where it struggles, just because of the amount of data coming in from the laser scanner. So you can still use these older systems for things like processing. It may take a little bit longer for this stage in the process, but that is something that we still are able to do. Now I'm going to go ahead and pause this until we finish off the rest of this so we don't have to sit here and chat. All right, so point fusing is done. And at those lower numbers, you can see, again, we've kind of got that orange peel to deal with. Let's rotate this around. They're not connected, so I can use this option here to select this upper section. Now, if the upper section and the table aren't connected, if the little caps I used are large enough, so what we can do, I clicked again. Let me give it a second to think. So what we can do with this connected section is use invert, which will select everything else but the main part, and just hit delete. So that's a quick way that we can clean up that area. And then we'll go through, again, isolation detection. I'll put it back to the default at 15. Overlap detection. In this case, I'll run smoothing, again, because we kind of did it on everything else. Again, strength is relatively low. I don't want to be too aggressive. Pay close attention to the sharper corners. Make sure that we aren't essentially melting them. And then we can move on to the meshing stage. So for the meshing stage, now I'm going to go back to that 0.2 millimeters, which is what I did both of the other examples at. Now, we took the original scan, again, set at 1 millimeter, but captured enough data that we could fuse it at 0.17, 0.19, somewhere around there, fused at 0.2. And now I'm mimicking that same grid size of 0.2 to get to the meshing stage. Not generally how it has to work. Again, what I would say more times than not is it's going to come down to the level of detail you need from your scan. It's not going to magically make more detail for you. If you don't have it at the point cloud level, it's not going to just magically get better. But we are able, in this case, we took the same exact scan that was just producing kind of meh results. And now we were able to change some of our settings. And now we've got a pretty nice uniform grid. There's a lot of noise in it so that we can filter out, but we do have a pretty nice uniform grid. So the next step for me is I'm going to run through isolation detection. Again, it may or may not find anything. And then the fill holes, this is where it kind of gets a little tricky. Fill holes is going to be tough because of all of the noise in these areas. So it might be good to use a smoothing brush in this area, for example, maybe down here, everywhere that we had marker dots, kind of go over and smooth those areas. Instead of removing them and trying to patch them, just kind of taking it like that. And then this one right here, maybe smooth it a little bit more. You don't want to get too close to the corner, because once you get over that transition, it's going to be all bets are off. And then I'm going to find these tiny holes, and then we'll fill those in. So let's go ahead and zoom in. There. All right, just a couple of those. All right, so at this point, it still looks pretty bad. But when we're going to go through the smoothing, we're going to apply the smoothing. Again, at the mesh level, it's not quite as aggressive because we've got so many triangles. It's going to really respect the angle, look at the angle between them. So pay close attention to areas like this where we've got that sort of formed recess. And then we can just continually apply smoothing until we're happy with the results. Now, with all of the settings that we've used, we can still see kind of that orange peel. And ultimately, what I would say is the mesh density of 0.2 is probably a little too small. Probably want to make it a little bigger. So if we go to simplify, and let's take this up to 60%. Actually, let's go to 25%. So right now we're at a little bit over 1 million polygons, 1.1 million. So when we will look at this ratio, essentially we're saying we want it to be 25% of what it is right now. The default is 40%. So now you can see we took it down that 25%. If we apply it again, it's just going to continue to reduce it. With most things we can undo. That's not universally true. We can always go back to the raw data, but some steps or some parts of the process you won't be able to undo. In this case, I'm just going to continue to refine it. Take a look at the polygon numbers. Now we're at 300,000. And now that they're a bit lower, this means that these bumps in the surfaces are more gradual, which means we can go back to the smoothing step and we can reapply smoothing with the lower number of polygons. And you can see we're still keeping those sharper transition corners, but we're smoothing out the tops. So again, I'm going to apply it one more time. And I think that's a pretty good result. I still have good detail on those corners. Of course, we're missing a bunch of data just because of the way I scanned it. This part I would, even though it picked it up in shiny black, I would probably use scan spray. It would help in these sides and these corners. And again, I would scan it multiple times, probably raise it up a bit more and use some 3D marker blocks, things like that to help get these sides better. But that wasn't really the point of the video. It was really to focus on getting a clean final result. All right, so let's take one last look at, again, the raw data. So this one's scanned at 0.15. You can see there is a lot of texture on the surface, and the final mesh surface, again, looks pretty smooth. The 0.5, if we look at the raw data, again, it's got a lot of texture on it. The settings for fusion, in this case, we fused the distance at 0.5, so the fused version of this is a bit smoother, and the meshed version is smoother still. This one is probably retained the least amount of detail on the edges based on the settings that we used. And then the final version here, this one was scanned at 1 millimeter, so its raw data contained the least number of points, even though all three were relatively similar based on the amount of time I spent scanning. The fused version of it, when we redid it, it fused it at 0.2, which was the same setting, or in this case, that 0.2 was the same setting that we used to refuse it the second time. And then the meshed version looks pretty good. Again, it retained those details, the sharp sort of transitions and corners. They're not crisp because it's a formed metal part, but it did maintain essentially what is some consistency in these corners. So I think, let's go ahead and rotate them all to be about the same. Let's pull this one over. So I think out of all three of these results, God, it keeps rotating it that way. That's really annoying. But I think out of all three of these results, I would probably say that this part, because of the geometry and the nature of it, I would default to scanning it at, say, a 1 millimeter grid or a 1 millimeter setting at the scanner and fuse it somewhere in the 0.2 to 0.5 millimeter range, which would give me a pretty nice, consistent, dense grid that's tight enough to capture all of these details. And then when we move into the meshing stage, that we can have a grid size that is reflective of the amount of detail that we need. So in this case, the grid size of 0.2 gives us all the amount of detail that we need. Now, of course, if I had captured everything on the outside, then it would be better. Now, even though we are missing data here, we can still do things like come in and try to fill all these holes with curvature-based holes. And in some cases, it might be okay. It might be able to fill in that data and smooth it out. I'm going to go ahead and this one on this side, probably less so. It actually doesn't look too bad. We'll do this one over here. So even though I am missing a good bit of information on the side, on these sides based on just the way I scanned it, I am able to kind of put it back together, and you could, again, rerun smoothing and things like that. If you remesh it, it's going to go back to the fused version of the points. But if you rerun smoothing and simplification, then you're working with the current data that you have. All right. I know that was a lot. This part of the video in the software here took over 45 minutes. It wasn't what I was expecting, but it is a lot to digest. So the key takeaways here are to not get too bogged down at the scanning level, setting that point distance so small. Think about the amount of detail that you actually need for your part. If you've got a soft formed part like this, not soft as in the material, but the geometry is not hard, sharp corners. If you got something that has rounded transitions and has mechanical features, but you're not trying to pick up minute casting details, things like that, you don't need to go overkill with the amount of frames you capture and those settings. So think about something in the like 0.25 to 0.5 millimeter range for most like mechanical type parts, 0.5 to 1 millimeter range for parts like this, and even bigger if you've got more broad shapes like a car fender or something like that. When you go to the fusion section and you're trying to build out a clean point cloud, keep in mind that you want it to be small enough to capture the required detail, but large enough that you don't have a ton of work to do with smoothing and things like that. I would still suggest to avoid simplification for 99% of scans. I haven't found a good use case for it in the stuff that I scan. So I typically will do isolation, overlap, smoothing, skip simplification, just because I don't like what happens to it at the meshing level. And then when we move into meshing, think about the grid size that you need to capture the detail. Remember that grid size can be smaller than the fusion distance that you use for your points. It will fill in the gaps of that detail, but there are going to be some diminishing returns. So if you don't have a point cloud density that's small enough to capture the details you want, adding more triangles by making them smaller is not going to magically create edges that didn't get scanned. You're not going to create sharp corners where they don't exist in your scan data. Smoothing at the mesh level is much less aggressive than smoothing at the point level. So at the point level, make sure you keep the strength low, increase the number of times it goes through. At the mesh level, you can crank them all the way up and pay close attention. But from what I've gathered, the algorithm for dealing with smoothing at the meshing level seems to do a better job at preserving the edges and corners. And then simplification is a reduction of the overall polygon count. You don't need millions and millions and millions of triangles to capture a part like this. It could easily be in the 50 or 100,000 polygon range, up to 250,000 polygon range. The smaller you can make it, the more performance you'll gain when you move into CAD. If you're using Fusion or anything else, most traditional CAD programs do not like meshes. And so keeping it as small as possible is only going to help you downstream. So make it as big as it needs to be for the detail you want. But if you can simplify it down to 90%, like if we simplify this thing again, and we can still keep these sharp, crisp edges and the amount of detail that you have in those corners, there's no reason not to do it. In most cases, if I am going to, let's say, Revo Design or Quick Surface Light from here, in most cases, I will take a higher density mesh and I will reduce it in those programs like Quick Surface Light or Quick Surface Pro. If I'm going directly from here to somewhere like Fusion, then I will make sure that I make this as small as possible. So if I reduce this again, let's see how far we can go down. I'm kind of just looking in these areas here. Let's turn this back off. All right, so we're down at 40,000 polygons, and I think there's still enough detail there where I could recreate this part. So it doesn't really need to be super detailed. So hopefully that kind of helps. The initial one we had was like 1.1 million polygons, and this one's 40,000. And there's really no issue with the quality of it. And the benefit here is the lower the polygon count gets, the better quality it's actually going to be in terms of those big broad surfaces. They're not going to be as wavy or have as much noise to them. They're going to get smoother. All right. So I think that's where we're going to end it. If you have any questions on this, leave a comment. Please let me know. Remember, we are, again, a Revopoint affiliate. So if you are purchasing and you do want to support the channel, I'll leave all that information in the description. We're also a Quick Surface affiliate. So you can use a code LEAD10 and save 10% off. I'll leave that information in the description as well. And as always, thanks for watching. We'll see you in the next one.